Yeah, as long as I get done, 8 minutes late, that'd be perfect. Huh, what? All right, we'll get rid of that. Okay, this is the Tech Math 3 Pre-Calculus class combined. We're in section 9-6, and we find that we have a rule that says if what? If x is equal to y, then it has to follow that the log of x has to equal the log of y. Isn't that convenient?
Okay.
Yeah. I mean, if it, think about a world where if x were equal to y, but the log of x wasn't equal to the log of y, wouldn't that be a confusing world? Yeah. I mean, I'd have to redo all my calculators and everything else. It'd be really bad. Well, that's the only theory in this chapter, so I guess we'll do what we normally do and solve problem number 2. I know, not much. 5 to the x is equal to 38.1. Well, we could just take our calculator and we could turn it on and we could say, oh, I bet you it's something bigger than 2. Right? Because 5 squared is 25, and it's obviously something smaller than 3 because 5 cubed is 125. So I could say 5 raised to, oh, that's 2 5s. 5 raised to the 2.3. 40. Oh, okay, so it's not that one. 5 raised to the 2.26. 37.99. Okay, so the right answer is x is equal to 2.26.
So this is just guessing?
That's what I just did. Yeah, I just guessed.
I was just curious.
Isn't that cool?
I know that sounds a
Yeah.
little stupid. I just wondered it out. But I mean, so basically, all we have to do is think of a number that sounds good that makes that number.
You could do it that. I'm just saying you could do it that way. Yes.
I think it's going to give us multiple.
You don't have to do it that way. Yeah, but I'm taking, on the SAT exam, and I just got through reading the thing about the covered wagons crossing the plains, and I'm really bummed out. And I get to some math problem, and I want to take my time solving it, so I just guess until I get the right answer.
Did you do an ACT math prep class?
Yeah, I could. Yeah, why not? Yeah. Okay, so we're in chapter 9. In chapter 9, how would I solve that problem? Well, we only have one rule, right? The law, if x is equal to y, here's x, here's y, they're equal, then that means the log of 5 raised to the x has to be 38.1, right? No, log of 38.1. And then we remember from our previous chapter that if I have an exponent inside the log, I can bring it out, and I can say that's log x log 5 is the same as saying log 5 raised to the x. That's perfectly okay. Is log 38.1. And then I can divide both sides by log 5. Log 38.1 divided by log 5. I can then put it in my calculator, and if I do, I'm going to get 2.26. I am? That's it. Where's my log? Log 38.1 divided by log 5 equals, 2.26. Wow. Now, was it easier to guess, or was it easier to do that? Pretty easy to guess. Yeah, that was pretty easy too. Now, the real question is, did I put that in my calculator? No, of course not. No, I put in natural log of 38.1 divided by natural log of 5. That's what I put in my calculator. Now, why did I put that in my calculator? Well, my calculator, if I hit the button once, I get a natural log. If I hit the same button again, I get common log. That meant I would have had to do 2 extra keystrokes to solve the problem, right? I mean that. And, oh yes, I mean my finger. I could have wore out my finger. I could have got a blister on it. I mean,
Even broken your finger.
I mean, all kinds of nasty things could have happened. So actually, because the common log divided by the common log is the same as the natural log divided by the natural log, I could go either way. But when I exactly, it's the same answer. Exactly, yeah. So if I had a calculator that could do log base 3.725 of 38.1 divided by log 3.725 of 5, I would get the same exact answer too. I don't have a calculator that can do that, but if I had one that could, I'd still get the same answer. Yeah. All right. So there's always another way to work the problem. I chose to use natural logs instead of common logs because it saved a keystroke. Yeah. And back to the SAT ACT situation, in 5 weeks, 1 hour a day for 5 weeks, I changed my son, who at the time was a senior in high school, his math SAT score by 150 points, and changed from going to some community college someplace to going to the University of Connecticut. So, and it has to do with practicing for the test itself. The test they ask on those two, on the SAT, ACT, is not the math we teach you. So you have to be taught that math in order to do well on it. All right, back to what we're doing. Are we doing anything? Oh, number 8. 2 to the 2x plus 1 is equal to 5x. Oh, well, can't have everything, right? Can I guess this one? Yeah, probably not. Okay, so I'm going to take the log of both sides. 2x plus 1 log 2. I'm skipping a step. If anybody wants me to put it back in, I will. X log 5. Want me to put in the step I left out? Log 2 to the 2x plus 1 equals log 5 to the x. There, I put in the step I left out. Is that better? All right. So now I've got that. Now I'm going to go and cross multiply some. 2x plus 1 divided by x is equal to log 5 divided by log 2. All right, so now I'm going to go log 5. I can find the right button. Log 5 divided by log 2. And I end up with 2.322. 2.322. All right, does it say how many? 3 significant digits. So I'm going to keep 4 significant digits, so I have 3 in when I get done. Okay, so now I'm going to go so and say 2x plus 1 is equal to 2.322x. And then I'm going to say 1 is equal to 0.322x. And I'm going to say x is equal to 1 divided by 0.322. And then I'm going to change my color and write down the final answer. All right. 1 divided by 0.322 equals. I'm going to go 3.10. But I'd be perfectly happy with a 3.11. So, because I could have round, depending on who taught you how to round. The Cordoville rounding rule says if I have a 5, then I round up if I'm odd, and I roll down. I round down if I'm even. So I call a 0 an even number and not do this. But you could have been taught that if you have a 5 there, you'd round this up, and that'd be perfectly okay too. Right? So I didn't guess on that one. I apologize. 3 point. Who would have guessed 3.11 anyway? Anyway, it could have happened, I suppose. Solve for x. All right, back in operation. We'll look at 22. 22. E to the x over 3 equals 47.2. Now again, I could use common logs, I could use natural logs. I'm going to use natural logs. Natural log e to the x over 3 is equal to 47.2, natural log 47.2. The natural log of e raised to the exponent is just going to be that, and natural log 47.3, and I'm going to have x is equal to 3 times the natural log of 47.3. And I'm getting ready to write down the final answer as soon as I put it in my calculator. 3 times natural log 47.3. 4 significant digits, 11.57. 11.57. Is that what I wanted? 4 significant digits. All right. I could do it using common logs, so we'll rework the problem. Which problem was it anyway? So I could take e to the, I could take that is equal to 47.2, and I could say x over 3, the common log of e is equal to the common log of 43.7. I could do that. Okay, now I need the common log of e. Okay, so I'm going to take the log of 2.718281828, because I remember that's what it is. And I'm going to have x over 3 times 0.43429 is equal to, and I'm going to take the common log of 43.7 and come up with 1.64048. I'm going to say x is 1.64048 times 3 divided by 0.43429, and then I'm going to keep 4 significant digits when I get done, times 3 divided by 0.43429. Boom. And I get 11.33. Did I get 11.33 before?
Nope. Because you got 43.7 is 42.47.
Oh. What kind of learning disability is that? I forget. 7.3. Boom. Log 47.3. 1.67486. 7486 times 3 divided by 0.43429. Boom. 11.57. 11.57. So I could have done that, yeah. Yeah, go ahead. Yeah. So I could have done it using natural common logs. That would have made it harder, because I would have had to remember what e was. Well, I could have gone and found out what e was. I could put a e to the 1 right in my calculator. Would have told me what it was, so I didn't necessarily have to remember. All right, let's try 40. No, we're not going to try 40. Yoda says no try. Do, don't do. So we're going to do 40. 28 divided by 56 is equal to 1 minus e to the minus x over 10. All right, well, I didn't write down the problem exactly as written, but I got pretty close, right? So this is 1/2. 1/2 minus 1 would be minus 1/2 is equal to minus e to the minus x over 10. Can I take the log of a negative number? Log of minus 1/2. Can I do that? No, not allowed. Not allowed. All right, well, I'll just multiply both sides by minus 1 and make them both positive. Oh, isn't that nice? Natural log of 1/2 is equal to minus x over 10. If I could write a 10. I could say 10, I just couldn't write it. So the natural log of e raised to something is the something. So I can just write down the something. So x is equal to minus 10, the natural log of 1/2, and now it's time to put it in my calculator. Okay, natural log 0.5 times, well, I can do the times 10 in my head, 6.931, and I'm looking at 4 significant digits again. And we should probably check our work. That'd be a cool thing to do, right? So, is 28 equal to 56 times 1 minus e to the minus 6.931 over 10? Okay, is it? Huh. How close do you think we have to be to say it is? Now, within 10? Within 5? No. We'll figure out how close we are and then decide whether or not that's close enough later. Okay, that seems reasonable. All right, so I got 56 times, close parentheses, 1 minus exponent of e to the minus 6.931 divided by 10, close parentheses, I think. All right, and I get an answer of 27.99867. Close enough? All right. Close enough. Right, good, close enough. 17 years teaching at Iowa Western. I've never used CE for close enough. Okay, this is a new leaf I'm turning over.
We are pioneers.
Yeah, we are pioneers in the training of these particular things. Yes. How far are we going?
Okay.
51.
Can we put CE on our tests, like to say close enough?
Oh yeah,
Okay.
yeah. And I'd only, instead of taking away minus 0.5, I'd only take away minus 1/2. Yeah, no problem. I could do that. All right. So we'll do 52 next, and then move on to the next section. 52. All right. Now we have that 15 is equal to 10 minus parentheses 10 minus 20 e to the minus t. Is that a t? Minus t divided by 15 microseconds. What are we solving anyway? For the following equations, use the following, find t. There it is. I found it. So I have,
Is that 52 you're writing down?
Oh, I hope that's 52 I'm writing down. Do you think it's not? Yeah. V naught is 15, EAS 10, EO 20. Yeah. So anyway, I got to solve for t. One equation, one unknown. What could be more simpler than that, right? All right. So let's see. I got a 10 here. I'm going to put on the other side of the equation. So I got 5 is equal to, I've got a minus 10 with a minus sign. So that's a positive 10 e to the minus t over 15 microseconds. So that's my first simplification. I'm going to bring the 10 on the other side. 1/2 is equal to e to the minus t over 15 microseconds. Okay, I'm now going to take the natural log of both sides because I'm in the chapter that tells me that that's what I'm doing. Okay, the natural log of 1/2. Anybody remember that? 0.5. Natural, no, 0.5. Okay, so that's minus 0.693. Now I'm only gonna carry 4 significant digits because my final answer is going to be in 1. Natural log of something raised to the e powers of something minus t divided by 15 microseconds. Okay, so t is equal to 0.6931 times 15 microseconds. Okay, so we can ignore all the units. Our answer is going to be in microseconds, and we're going to want 3 significant digits times 15. 10.4. 10.4 microseconds. Okay, good enough. Now it would have been much better to have one equation, 2 unknowns, and then we could have said, oh, I can't solve it. Yes, what's the question?
How did, when you had a 5 equals 10e to the whatever, and then you went down another step?
From here to here? Yeah. See that 10?
Yeah.
I divide both sides by 10. And this becomes a 1/2. And this becomes a 1. Yep. Clear as mud.
What was the final answer?
Who cares? Oh, 10.4 microseconds. And the front row should have been able to guess that one. I mean really, this is a...
0.00000061.
Yeah. So if we come back to 1/2 is equal to that, well, never mind. I was having a random thought. Okay, now we're in 9-7, and we're not going to be in red very often because that's not good, right? Red. So now we got something that says, gee, if I have the log of some base of x is equal to the log of some base of y, then it must be that x is equal to y. Didn't we just say that in 9-6?
Yeah.
No, we said if it's xy, then the logs of 1 is it. But it sounds to me like it's almost the same thing. Yeah, it must be the same thing. And then we've seen this before, I'm pretty sure, that if I have y is equal to the log base b of x, that's the same as saying x is equal to b raised to the y. That these two equations are the exact identical equations written in different ways. So that if I can't solve that, I can solve this one. That's what I would do. Okay, so that's what we're doing. And I don't believe we only go to problem 33. All right, so we'll try to do problem number 2. Oh, no, we won't. We'll just do problem number 22. Number 2. Number 2, my mistake. Log of 2x plus 1 is equal to the log of 4x minus 5. Oh, 2x plus 1 is equal to 4x minus 5. 6 is equal to 2x. X is equal to 3. All right, check our work. Is the log of 7 equal to the log of 7? Yes, it is. Oh, must be right. So because I'm in section 9(7), and I remember that if the two logs are equal and I have the same base, then the two, what are those things called? Arguments. The two arguments have to be equal as well. All right, we move down to 12. Log 2x plus 1 minus log x minus 4 is equal to log 3. Wait a minute. No one told us we could work that problem. But from a previous section, we know that if I subtract logs, that's the same as dividing. So I can write this as log 2x plus 1 divided by x minus 4 is equal to log 3. Now we have some argument is equal to some argument, and the logs are the same base, and I can just write down 2x plus 1 divided by x minus 4 is equal to 3. Now we can just guess. Oh, I guess not. All right, so I got 2x plus 1. We can cross multiply. How's that? 3x minus 12. So I got 13 on this side, and I have x is equal to 13. And we say, well, we better check it, right? X is equal to 13. So is the log of 27 minus the log of 9, is that equal to the log of 3? Well, subtracting logs is the same as dividing. 27 divided by 3 is 9. So in this right here, I have log 3 is equal to log 3. Check. So I'd be okay there. I guess we need some natural log guys. We'll do 22. Number 20. I said that before, right? Number 22. Natural log x minus 1 is equal to 2. Oh, we can't do it because this isn't, I don't have log on both sides, right? Well, yeah, but this is the log guy, and we can write it as an exponential, right? Okay, so this says that e squared is equal to x minus 1. So I'm using the equation on 3, 2, 8, which says if y is the log base b of x, then x is b raised to the y, or whatever it's got. All right. So x is going to be e squared plus 1. And, oh, we're done. It doesn't say find it to two significant digits or anything. What's wrong with that answer? Is there anything wrong with that answer? Oh, that's wrong with that. That's perfectly okay. Or we could write 3.718281828 if we wanted to, and then we could say, well, maybe we only have two significant digits. We could do that too. So this guy unsat too many digits. Either one of those guys would be perfectly okay, considering that we only have one lousy significant digit in the problem. Even a 4 would probably be okay. 4 might be okay for that one. But e squared plus 1 would be the more elegant answer. How's that? This guy here would be the most hosed of all the answers, because we don't have 10 significant digits. Those guys would be perfectly okay. That guy would be most elegant. Okay. Guess we'll do 36. Well, I don't know. We might be going too fast. You think we're going too fast? Might be going too fast. I don't know. We'll do 30 next. The log. Why is it always 2x plus 1 anyway? This author can only write one thing. 3 log 3 is equal to 3. Okay, so I'll rewrite it. Log 2x plus 1 is equal to plus. Good thing Raimundo isn't there. He asked what that symbol is. Plus log of 27 is equal to 3. When I add logs, it's the same as multiplying. Log of 54. 54x plus 27 is equal to 3. So that being the case, 10 cubed is equal to 54x plus 27. Okay, so that'd be 973. 973 divided by 54 is equal to x. X is equal to 973. Somebody turned off my calculator. 973 divided by 54. 18. Yeah, 18. Why not? All right. Come back up here. The log of 18 times 2 is how much? 56 plus 1 is 57. 57 divided by 27 is equal to 3. Question mark. I don't think so. What's wrong with that? What's wrong with that is I'm multiplying, not subtracting. 57 times 27. I don't think that's right. That might be. Yeah, it might be right. Who knows? 57 times 27 equals log answer 3.18. Good enough? 3.18. Yeah, probably good enough.
It's supposed to be 54.
Oh, now you tell me. What's the problem?
I'm a green writer.
Yeah, but what is it? 18. What's 18 times 2? 36? So it should be 37. 37, right? 37 times 27. 37 times 27 equals log second function answer equals 2.9995. Like that. Yeah. So if you're going to check your work, you should check your work using the exact same problem. Sure, I'm glad we figured that one out. Okay. All right, on to 36. Number 36. Natural log of x plus natural log 2x minus e minus 2 equals natural log 3 Okay, so we'll rewrite that as natural log of x times 2x minus e divided by 3 equals 2. Okay, so the minus 2 goes on the other side of the equation. Natural log 3 becomes a negative sign, which means it's a divided by thing. And now we get that. We're going to go and raise both sides to some power of e. And we're going to get x, 2x squared minus ex is equal to 3e squared. Skipping a couple steps like I normally do. If I skip too many steps, just tell me, I'll put them back in. Alright, well, what are we going to do about that? 2x squared minus 2.81828, as I was saying, 2.71828 x is equal to 3e squared. Okay, so 3 times e squared to 2.2. 22.17. Go with 22.17? Yes, we will. All right, now I'm just going to put it in my calculator. Second function, polynomial solver, first degree polynomial. The a is a 2. The b is a minus 2.71828. And the c is a minus 22.17. Okay, and then I hit the solve button, and it says I have x's that are two different types of x's. Okay, so I got a minus 2.7185, and my other x is a 4.0776. Now, because we can't have a negative log, right? If either of these answers, when we put it back in the original problem, comes up with a negative thing inside the argument for the log, then we have to disallow it. It's not an answer. Okay, so now we're going to go back up to this top and say, oh, look at that. If x happened to be the negative 2.7, then that's not allowed. So we'd cross that out. That's not an answer. But the 4.0776, if I put that in, I'm going to end up with positive arguments for my logs. That's perfectly okay. Okay, so there are several cases that could be. So sometimes you get an answer where if that were the right answer, you'd be dividing by 0. That wouldn't be allowed either. Okay, in this particular case, if you come up with a negative log, then that wouldn't be good. Okay, moving on to section 9.8. And here we have money. So I could have exponential growth. Y could be equal to a e to the rt, where a is some amount and r is some rate of growth, and I'm growing. Or we could have exponential decay. Y could equal e to the minus rt, where I'm decaying something. So if I have some plant growing, I have exponential growth. If I have some pile of radioactive material in the room, then I would have decay. So I've got, see my briefcase there? The case that the computer came in. Right, sitting there on the desk. Okay. It has radioactive material in it. Okay. And that radioactive material has a half-life of 30 seconds. Okay? So we have case 1. That's case 1. I come in the next day and I have a different case, and it has radioactive material that has a half-life of 20,000 years. Half-life, 20,000 years. Which case would be more dangerous? the half-life of 20,000 years would be a non-event
Oh, no, you're right.
because it's decaying so slowly. The radiation isn't going to affect you in the hour and a half that you have me in the class. The 30-second half-life, however, means you're all dead
Yeah.
within a minute and a half. Yes. I mean, we'd probably be dead before our next breath type dead. Yeah. That would be a huge amount of radiation exposure very rapidly. There's not the last Russian submarine to go down, but the one before that was I forget what it was, but the Russians, when they made a submarine, let's move back. In American society, is life worth anything?
Yeah.
Yes. In Russian society, is life worth anything? Okay. So in general, that's the case. That's right. So in Russian society, to send 20 million people to the gulag to die in the winter, no one's going to care. Perfectly all right. All right. So when the last Russian submarine went down, the admiral in charge said, "Why do I want to rescue those guys? I can't have my submarine back." That would be an attitude that an American admiral would never have. The American admiral would be, you rescue the crew. In the Soviet Navy, when you enlist in the Soviet Navy, it's for 20 years, your first enlistment, and that's on a boat. If the boat gets decommissioned, you're out. So if you enlist for 20 years, the boat lasts for one more year, then you're out of the Navy. You don't have a job. You don't move on to a different boat. You enlist, you go to a boat, that's your boat. So the crew is totally expendable if I don't have the boat anymore. Anyway, the Russian submarine before that went down, when the U.S. builds a submarine, we have the reactor material, and we have a primary shielding that protects around that material, and then we have a secondary shielding that protects us from the radiation that gets to the primary shielding. So when the reactor is critical, inside the reactor compartment, inside the secondary shielding, you have 100 rems of radiation. The dose that kills off 50% of the population in 30 days is like 300 rem. Okay, so people are not allowed in there. The Soviets don't have a primary shielding. The Soviets only have a secondary shielding. Their crews get submarine pay just like our crews do, but their submarine pay is called sterilization pay, because that's what's going to happen if you're on board for 20 years. Anyway, that's just a different philosophy. One of the lieutenants, a 22-year-old guy, during the casualty, went inside there and shut a valve. Okay, and that stopped the leak. That saved the Russian submarine from sinking for another 30 minutes or so, maybe longer. Saved the submarine a little bit longer. He then, after he went in the reactor compartment and shut a valve, he came out and sat in the wardroom talking to his friends. As the flesh melted off his body, he was still alive. The flesh melted because the beta radiation that he was exposed to was such a high level. The beta radiation doesn't penetrate the skin, okay, but he ended up with alive, having his flesh flow off his body. Very impressive thing. And then, of course, all but 2 or 3 guys died anyway. So death is only death. Doesn't really happen. So what if you die because of the radiation poisoning, or you die an hour later because the boat goes through crushed depth? I mean, no one's going to care, right? You're dead either way.
Is there like a movie about that?
No, not yet. No, it's too gruesome to make a movie about. Yeah, the movies are never realistic. They don't tell the whole truth. Yeah. Now, back to the last submarine that went down, seeing that we're on that issue. There's Norway, there's Russia, there's the submarine that went down. The U.S. submarine rescue material, we're the only people in the world with the equipment to rescue people from a downed submarine. Okay, in the Atlantic Ocean, there's only 5% of the ocean that you can actually be on the bottom of, and it's shallow enough to be rescued out of. Right. In the Pacific, it's only like 2% is only shallow enough to be anything. The other 95%, 98% is too deep. The boat's going to implode, and it's going to spread itself across the bottom. Anyway, our submarine rescue equipment is sitting over here in San Diego. Okay, the only way it's going to get to Russia on time is if the watch officer at ComSub land. So here we are in Norfolk. And this is an 06 watch officer at ComSub land. Pretty senior guy. The only way it's going to get there in time is if he orders it to leave. Okay, there are C5s standing by at an airfield for it to be loaded on, but it's not routinely loaded. He'd have to order it to be in the air. When that order didn't come, it was never loaded in the air. The planes were never loaded. They weren't loaded for 24 hours. At the end of that 24 hours, there wasn't enough time to get from San Diego into some place in Norway and get it off there to rescue the guys. The guys stayed alive for about 3 days. The couple dozen that were in the engine room did. It would appear a torpedo blew up in the torpedo room, is what happened. You have to be really, on an order of stupidity, allowing your own torpedo to blow up in your own torpedo room, that's pretty big, right? That's why you stay on the same Russian submarine for 20 years, so you're not that stupid. But what happened is that we delayed. United States, we delayed. And because we delayed, we couldn't get there in time. We're the only guys with the assets to get there. And that was really stupid. We changed our procedures, and the procedures now say, doesn't matter what country it is, as soon as we know a submarine's down, we're moving the equipment. Because we can always recall it.
Yeah.
It's in a C5 flying across the ocean. It can land in Pearl Harbor. It can land in Hawaii. It can land in Guam. It can land in Germany or in any place in the world. It doesn't have to necessarily get there. But if we want to get there in time, if there's any chance of getting there in time, we have to do it now. All right, now what does that have to do with Chapter 9 of the Tech Math book? Hard to say. Oh yeah, exponential growth and decay. Okay, so here we are. This is the Shroud of Turin sitting here. And got a picture of somebody on the shroud. Hey, there we go. And we're going to carbon date it. So the idea is that carbon-14 is made in living organisms. It is made by the sun's radiation. Okay? The natural occurring carbon-14 that was here 4 billion years ago is all gone. Okay, so it's in some equilibrium amount in the world, and when I fix it in the living organism, it doesn't change; it only decays. Okay, so that's the principle. I'm gonna take a itty bitty piece of this down here so it doesn't hurt anything, and I'm gonna test it and carbon date it, and I'm gonna come up with some age for the shroud. Okay, what age did I get? Yeah, I got about 1,000 years old. All right, what does that mean? That the shroud's 1,000 years old? That the mold on the shroud is 1,000 years old? That that means it's at least 1,000 years old. Yeah, that's one of the things it means. But unless we can have a bigger sample and we can clean it out and only get the shroud, we won't know. And no one's going to give it to us, so don't worry about it. But that's the whole theory, carbon-14 dating. So those of us that would agree the Earth is a mere 8,000 years old. Anybody think of that? No, perfectly okay to think that. The carbon dating works because when it was created 8,000 years ago, everything was put in so that it would show us the right results. Perfectly okay. If you want something, let's say I have something really old. I have something 300,000 years ago. Carbon dating going to work? No, it's not going to work. It's all gone already. Okay, so that's what that's all about. Now, if I have a capacitor and I'm charging it, I have some upper limit on how that charges. Okay, I've got a 5-volt battery here, and it's only going to charge to 5 volts. So I could have some exponential growth rate that has an upper limit. So on page 333, we have if I have something that needs an upper limit, 1 minus e to the minus RT is what I'm going to be using. So when I have a capacitor charging, that's going to be the case. If I have a population of human beings with a birth rate and a death rate, there's going to be an upper limit based on that birth rate and death rate. Okay, I'm not going to get to 500 million trillion human beings on the Earth. You do in Star Trek 1, they did that, right? They had a planet. What was that planet name? Started with a G. It's not Gideon. Yeah, it was Gideon. Yeah, it was Gideon. So Gideon population had grown to the point where every single inch of the planet had people on it. You know, and they needed the Enterprise to show up to introduce a disease so people could start dying off. Yeah. Well, that's not going to happen, so don't worry about it. Okay, so now we're going to work some problems. Now that I've goofed off enough. Did I goof off enough? Not. Oh, I need to goof off some more? All right. Who won World War II? World War II. Who won? Okay. So there's the U.S., there's the Germans, there's the British, there's the Russians, there's the Japanese. Okay, so those are our choices. Okay, show of hands. How many people think the United States won World War II? 1, 2, 3, 4, 5, 6, 7, 8. 8. How many people think Germany won World War II? You vote for Germany? How about the British? How many think the British won World War II? How about the Russians? How many think the Russians? 2? I think you already voted there already, Jeff. How many thinks Japan won World War II? No. Okay. That's the right answer. The think about yeah, obviously we're stuck on U.S. history, right? We have our history, rewrote our history, right?
Yeah.
7 December 1941, Pearl Harbor happened, right? Yeah, Pearl Harbor happened. Prior to that, what was our involvement? Well, prior to Pearl Harbor being bombed, what was our involvement in World War II? We gave 50 destroyers to the Brits. Yeah, we took some islands in the Caribbean from the Brits for the 50 destroyers. It's called the Lend-Lease program. We basically did squat. Yeah, squat. That's about it. In December of 1941, so here's Germany. Germany has expanded into Russia on 3 fronts: a northern front, a southern front, and a central front. Moscow was surrounded by a bicycle carrying rifle platoon. Okay. But the fact of the matter is, that's as far as they went. The Russians stopped them there. So the Germans in World War II put 950 divisions in the field. A division is about 10,000 guys, but towards the end of the war, it was slightly less. Of those 9,500 divisions, when we got around to invading Western Europe, France, there were 150 of them left. Who got rid of the other 800 divisions? Our pals, the Russians. Yeah. If the Germans didn't do something silly like invade Russia, then Russia would have invaded it a year later anyway. The battle still would have happened. But if we would have tried to land on the Normandy beaches with 900 plus divisions of German soldiers sitting there ready to reinforce France, it would have been a different outcome. Yes?
Have you ever read the, you know how we have our Medal of Honor?
Yeah?
You ever read any of the Russian equivalent?
No, I've never read the Russian equivalent one. But yeah, I can imagine.
He saved some guy and used his gun to give him cover fire.
Yeah.
The Russians is like he killed 84 people by himself and was gone for 3 days.
Yeah, exactly. It's totally amazing. One of the highest decorated tank operators in World War II was a Russian female. And of course, the females weren't allowed in the tank corps. Didn't matter. You know, you drive a tank, that's good enough for us. All right, back to 9-8. What am I doing? I'm going to 25. All right, we'll try number 4. The amount of bacterial growth in a given culture. Does that mean the Chinese and the Japanese culture? Is that what they're talking about there? Must be, right? Given culture, n is equal to n naught e to the 0.04 t. Why are we still alive as a civilization anyway? Haven't the viruses got to us yet? Seems like they have the upper hand here. All right. Where t is in hours, n is the initial amount, n is the time after that. How long will it take? How long will it take for 6,500? Okay, so I got this 6,500 e to the 0.04 t, and I'm solving for t. That's what I'm doing. So my final amount 10,000, initial amount 6,500. E to the minus of blah blah t, I'm solving for t. Divide by 6,500. 100 divided by 65 is equal to e to the 0.04 t. Take the natural log of both sides. Natural log 100 divided by 65 equals 0.04 t. T is equal to natural log 100 divided by 65 divided by 0.04. And when I get done, the answer is going to be in hours because t is in hours in the problem. Okay, natural log log 100 divided by 65, the whole thing divided by 0.04. Boom. 10.7 hours. 10.8 hours? 10.8 hours. I have 3 significant digits, I guess. It's trying to tell me that. In that 10,000, they say I have 3 significant digits there. So I'll keep 3 significant digits. All right. Harry, number 18. That'd be a good one. Number 18. Harry retires with an annual pension of $65,000. That sounds like a good idea. Anybody want to retire? And that'll be like $2.50 when you guys retire, due to inflation. But right now, $65,000 would be okay. With an inflation rate of 8%, how long will it be before its purchasing power is $50,000? Okay, so 50,000 is equal to 65,000 e to the minus rate. What's the rate? 8%, 0.08 t. That's what the problem's trying to tell us. All right, well, so I got 50 divided by 65. Natural log of that is, I'm skipping a whole lot of steps here, minus 0.08 t. T is equal to natural log 50 divided by 65 divided by 0.08 with a minus sign, which will make it all positive because the log of something less than 1 is negative. Okay, so I got log 50 divided by 65 divided by 0.08, boom, and I got 3.3 years. We'll call it 3.28 years. We'll call it 3.3 years. 3.3 years. And how long will it take to get halfway there? His money is only worth half as much as what it was. So half is going to be e to the minus 0.08 t. When was the last time the interest rate was at the inflation rate was at 8%? Jimmy Carter was president. I mean, you guys don't even remember. And I can remember. I have life insurance policies that I bought when Jimmy Carter was president, right? And so I have this $100,000 life insurance policy, and at the rate of interest that we're getting when Jimmy Carter was president, it would now be worth $10 million. At the guaranteed rate, which is 4%, which it's been at for a long time because the current interest rate is really low, it's not even worth $20,000 right now. But I was supposed to be a multi-millionaire. Now, what the country would have been a total complete wreck if the interest rate stayed at Jimmy Carter's, right? I can remember, anyway, never mind. You don't have to remember those things. So 8% is a huge inflation rate that you guys haven't seen in your lifetime. So natural log of 1/2 is equal to 0.08 t with a negative sign in front of it. T is equal to natural log of 1/2 divided by minus 0.08. So this is how long it's going to take for his money to be half of what it used to be. 0.5. This is why you don't retire in retirement. You continue on working. 6.7 years. 8.7 years. If I could read my own calculator. 8.7 years. So at an 8% interest rate, a fixed retirement is going to corrode very rapidly. Okay, enough of that. I guess we need to do some radioactive decay problem. I guess not. We'll do 20. Number 20. The discharge current of a capacitor, I is equal to 0.01 e to the minus 75 t. Find t in seconds when I is 0.004 amps. Okay, so I got 0.004 is equal to 0.01 e to the minus 75 t. I'm going to put this on that side. 0.4 is e to the minus 75t. I'm now going to take natural log of both sides. Natural log, if I could spell natural log. So t is equal to the natural log of 0.4 divided by what? 75 minus 75. All right, ready for my calculator. Natural log 0.4 divided by 75 equals 12.2 milliseconds. All right, now, what is this 75? This 75 is the time constant, RC, the resistance and the capacitance, right? We are looking for a time, the time when 0.01 would be all of it, 0.004. So that is going to be a time when I get, see, when t gets very, very, very large, then this one, yeah. I guess there's no way to make sense of the problem other than to solve it. So we'll remove those thoughts. There, those thoughts are removed. We'll just solve the problem and move on. I'm thinking that from an electronic point of view, the problem's pretty hosed. Number 22? Oh, no. We'll go to 28. Yeah, why not? Number 28. The natural log of A minus the natural log of 50 is equal to KT. All right, so I've got 50 milligrams of a radioactive sample of radon, and it decays. At the rate of decay, we have that. Where A is the amount remaining, T is the amount in years, K is a constant. So K is a constant, minus 4.10 times 10 to the minus 4th. Find the amount remaining after each of the time intervals. So we want to know how much remains in 25 years. Okay. A is the amount remaining. All right, so if we take natural log of A over 50 is equal to KT, and then we raise both of those as powers of E, we'd have A is equal to 50 E to the minus 4.1 times 10 to the minus 4 T. Okay, so that's what we have. And then we want the amount after 25 years. Okay, so we're going to have 50, and this is milligrams, e to the minus 4.1 times 10 to the minus 4 times 25. Okay, going to be pretty close to 50 milligrams, I would imagine. Okay, so 50 times e to the minus 4.1 double E minus 4 times 25, close parentheses, equals 49.5 milligrams. And this is why at the turn of the last century, the 19th century, 1900 or so, up to the middle of the 50s, we were putting radon in our watches so they'd glow in the night. We were putting radon on our lipsticks so they'd glow. Our lips would glow at night. It wasn't until 55 or so that we decided that, we're subjecting you to radiation poisoning. It's going to kill you off in 50 years because of cancers. Okay, so in a society where the average age is 45 years old, do we really care about the health risks of anything that's going to happen 40 years from now? Probably not. So 1850, it was perfectly okay to put radon on our watches and have them glow in the dark. 1950, perfectly okay to do that. We're all smoking like furnaces anyway. We're going to die of lung cancer before we're 60 years old. Why do you think the retirement age was 65 when Social Security was brought out? Because less than 1% of the population made it there. We're bringing. Think of a Social Security program. I'm the President of the United States. I'm Roosevelt, right? Theodore Roosevelt. Not Theodore. Who's the right one? It's the other one. Anyway, I'm President Roosevelt, and we're gonna start this Social Security system. We're gonna take money from every single working American and put it in the bank, so at age 65 we can pay out in a retirement system, right? And oh, by the way, 95% of you will die and not see a penny of it. Okay, raise your hands. How many want to be in this system? Yay! Won't it be great? Social Security, yay! See the problem? That was a very hard problem. That's a very hard sell. We're having that same sell now with this Obamacare thing. Okay, show of hands. How many want to double their medical care so we can take care of people that don't have medical charges? Wait a minute. Does that mean me? I got to do it too? So same type of thing. So right now, if we applied the rules that Roosevelt had at the beginning, and only 1% of the population is still alive when we start paying this off, we would be looking at age 85 for retirement, not age 65. Okay. That's one of those things. Got on hand. Okay, I think we are done for the day. Thank you very much. See you Wednesday.
My board.